Today, we're going to pull back the curtain on one of the most important yet invisible systems that keeps our modern world running and comfortable. We're diving deep into the engineering behind chilled water pipe design.
Seriously, think about it. You walk into a giant skyscraper or a shopping mall on a blazing hot day, and it's just perfectly cool. How does that even happen? Well, it's not magic, that's for sure. It's a massive, hidden network of pipes working around the clock.
And that engineering is a really fascinating game of trade-offs. It's a careful balance between physics, economics, and pure practicality to make sure everything is efficient and everyone is comfortable. So, let's get into the blueprint of how these incredible systems are designed.
Okay, first things first. Before we start crunching numbers, we got to understand the big picture. Let's take a look at the entire system from a bird's eye view.
So, at its heart, a chilled water system is just one big loop. You've got cold water sent out through supply pipes. That's the blue line. It travels through the building, soaks up all the heat, and then comes back as warmer water through the red return pipes. Simple enough, right? But this whole process is super regulated by industry codes, from groups like ASHRAE or under local rules like the Saudi Building Code. For any MEP engineer, the entire design really just boils down to balancing these four critical things you see here: the cooling load, the water's flow rate, its velocity, and the pressure drop. Nailing that balance is everything.
All right, so where do you even start with a design like this? Well, the very first step is always to figure out exactly how much cooling the building actually needs. That number tells us how much water we need to get moving.
And to measure that cooling, we use a unit called the ton of refrigeration, or TR for short. Just think of it as the fundamental unit of cooling power. It's the target we're aiming for.
Now, what's so cool here is how simple the main formula is. The water flow you need in gallons per minute, or GPM, is just the cooling load in TR times 2.4. And that 2.4 isn't some random number, It's a constant that comes directly from the physics of water, its specific heat, and a standard temperature difference used in these systems. This little formula, it's the absolute starting point for every single design.
So let's say our building needs 100 tons of refrigeration. You just multiply that by 2.4 and boom, you get your answer. The system has to be designed to move 240 gallons of water every single minute.
Okay, so we know how much water we need to move. The next big question is, how fast should that water be moving through the pipes? This is a critical decision.
This is kind of like a Goldilocks problem, There are industry standards that give us a target. For the main pipes, you're aiming for a speed of about 4 to 6 feet per second. If you go too fast, the system gets noisy and you waste a ton of energy on friction. But if you go too slow, you need much bigger pipes, and that gets really expensive really fast. The engineer's entire job is to find that just right sweet spot between saving energy and saving money on materials.
And that leads us to the final piece of the puzzle, and probably the biggest balancing act of them all: managing pressure loss. This is where things get really interesting, because this factor directly connects the pump you need to the size of the pipes.
So, as water flows, it naturally loses pressure because of friction with the pipe walls. Engineers have a special way of measuring this. They call it feet of head. It's a bit of a weird unit, I know, but just think of it as a way to talk about pressure. And a really common target, kind of a rule of thumb for designers, is to aim for a loss of about 4 feet of head for every 100 feet of pipe.
And this right here is the heart of the economic decision. It all comes down to this: pay now or pay later. If you're okay with a higher pressure drop, you can use smaller, cheaper pipes right now. But you'll need a bigger, more powerful pump that will use more electricity for years and years. On the other hand, if you want lower pressure drop, you have to buy bigger, more expensive pipes up front. The payoff? You can use a smaller, way more efficient pump that saves a ton on energy bills over the long haul. It's that classic battle: initial cost versus lifetime cost.
All right, enough with the theory. Let's put all these pieces together and walk through a quick, real-world example to see how an engineer actually makes the final call.
When you break it down, it's really just a simple 3-step dance that every MEP engineer follows. First, you calculate your flow rate. Second, you pick a pipe size based on your target velocity. And third, you double-check to make sure the pressure drop for that pipe size is right where you want it to be. Let's see it in action. Let's say we have a 150 TR cooling load. Step 1, we calculate the flow. We take 2.4, multiply it by 150, and we get 360 GPM. Step 2, we look at our engineering charts, and for 360 GPM, keeping our velocity in that 4 to 6 feet per second range, it points us straight to a 4-inch pipe. And for step 3, we check our numbers, and a 4-inch pipe with that flow gives us a pressure drop right around our target of 4 feet per 100 feet. Bingo! The design checks out.
And that's really how it's done. A few key formulas, a couple of critical decisions, and you've engineered a system that keeps us all comfortable without us even knowing it's there. It kind of makes you wonder, right? What other invisible engineering systems are hiding in plain sight, quietly making our world work?